Hello again, welcome to this A-Level Further Maths video. We're looking at the Core Pure Maths Book 1 content here. We're looking at Chapter 2, Section 2.3, which is to do with the modulus argument form of complex numbers, and we're going to be looking at what that is and why that's a useful thing for us to know about. So let's introduce ourselves to this by having a go at the question which is on the screen. Do you remember what the modulus and the argument of a complex number is? Well, that modulus, of course, is the distance of the complex number from the origin on the Argand diagram. The argument is the angle that that line segment there makes with the positive real axis. So I've given you a little picture to help remind you, but pause the video now and see if you can answer the question on the screen, please. Okay, so let's see if we can go through this together. Hopefully the picture helped us here. The picture here is just basically a nice right angle triangle, so we can use our basic trigonometry to answer this question. If we look at the cosine of the angle theta, the argument, we can see that that's going to equal the x, which is the real part of z, over r, the modulus of z. So x over r, and that must mean that x, of course, must equal r times cos of theta. So there's x written in terms of r and theta. Similarly, if we look at the sine of the angle theta, that becomes y over r. That tells us that y, the imaginary part of the complex number, can be written as r sine of theta, like that. So, did you get that right? Okay, let's see if we can actually now take this idea a little bit further. What I want to do is I want to just take my complex number z, which is of course equal to x plus I times y. And let's see if we can write it in terms of the modulus and argument here. So x, which is of course the real part of the complex number z, we could write that as r cos theta. And then y, which is the imaginary part of z, oh, there we go. We could write that as r sine theta. So we could write the complex number z in modulus arguments kind of a form like this. However, what we could do here is we could also factorize out the r, because I can see that appears in both terms here. So more commonly, we would write the complex number z as r times cos theta plus I sine theta, like this, where the number r here is the modulus and the theta here is the argument of that complex number. And when we do that, this is what we call the modulus argument form of the complex number. Okay, hopefully that made sense here. So what we're doing so far really is we're just kind of finding another way of writing complex numbers so that the modulus and the argument are clearer for us to see. So have a go at the question on the screen in a second. What you need to do is you need to work out the modulus and the argument of that complex number and then just write it in the appropriate form. Okay, so how did you get on with this one? I've drawn a little Argand diagram. We should always do that whenever we're trying to work out moduluses and arguments of complex numbers like this. So the modulus of the complex number, we're going to call that r. We can see just using Pythagoras theorem on this triangle here. We can see that's going to equal the square root of 2 squared plus squared here. So this length here is 2 and this length here is 3. Okay, so that's going to be equal to root 13. There's our modulus. Now to find the argument, we're after this angle here. So what I need to do is I just need to do a bit of trigonometry here. We're going to be looking at the arctan of 3 over 2 to find that angle. And when you work that out in radians, the 2 decimal places, it's 0.98. So with both of these numbers, we can now just write our complex number in modulus argument form. The complex number z, which is equal to 2 plus 3i, is going to equal root 13 times cos of 0.98 plus I times sine of 0.98, just squeezing it on the edge of the paper there like that. Okay, do you agree? Now, before we go too much further, I want to show you a feature on the calculator which actually allows us to convert numbers into modulus argument form on the calculator. So let me just show you here how we could have done that on the calculator. I've already put it into complex number mode, so I've already got that here, and I'm going to put in here 2 plus 3i in the calculator. It equals there, so that's in there. And now I can do a few things with this. If we hit the option button up here, you'll see on the screen there's a few different things which are just appearing. If I wanted to know just the argument, I could just hit number 1 there. If I wanted to know the conjugate of that, the real part, imaginary part, lots of things there. If I scroll down, you'll notice option 1 here, this puts this number into modulus argument form. The r and the theta are the modulus and the argument. So let's choose that, hit equals, and you'll see that there it is on the screen there on the display. The modulus of the complex number is root 13, and the argument there in radians about 0.98. So that's pretty useful, right? What about if we had a number in modulus argument form and we wanted to convert it back into our other form? Well, let's clear this away and let me show you how that might work. So let me just put in a number in modulus argument form here. So let's say we've got the modulus of 4 and an argument of, let's say, minus pi over 4. Now, how do I put that in? What I do is I hit shift and then this button here, and you can see here that little symbol, that's telling the calculator that I'm putting in the number in modulus argument form. Let's put in the argument here of minus pi over 4, and then we'll get the calculator to convert it for us into our regular form. And actually, if all I need to do here is press equals, and then it's put it there in our regular form. Again, pretty useful stuff, I think you'll agree. Okay, so let's just make sure that you can do that on your calculator, because it's a really useful thing to do. Pause the video, use your calculator, that function on the calculator, to convert these numbers into their various forms, and then restart when you're ready. Okay, I'm just going to write down the answers here that you should have got, just to make sure that you've got the same thing. So the 8 minus 17i, that turns into a number with a modulus of 353 square rooted, and an argument in radians to 2 decimal places here of minus 1.13. So obviously the calculator would have given you a much more precise version of that number, but this is what you should have written down for that one there. Okay, and then the one where we went the other way around, the 12 times cos of 2 pi over 3 plus I sine 2 pi over 3. Well, when you put that into your calculator with a modulus of 12 and an argument of 2 pi over 3, it should have just told you straight away that the number there is minus 6 plus 6 root 3 lots of I, and those are the numbers you should have got. Okay, so this is all really good work so far, but we might be wondering, why are the modulus and the arguments such an important thing to know about? Well, here, I want to show you something on the graph plotter here. So let me explain what I've got for you here. I've put 2 complex numbers, actually they happen to be real numbers at the moment, Z1 and Z2, and I've multiplied them together and I've plotted Z3 on the diagram as well. Okay, I've also put these numbers up here in their modulus argument form, so you can kind of see the moduluses and the arguments of these numbers quite clearly. And what I'm going to do is I'm just going to sort of move these numbers around a little bit. Now I've constrained the numbers, so I've constrained Z1 to always have a modulus of 3 here, and I've constrained Z2 to always have a modulus of 2. So if I just move that one around, you can kind of see here, I can move them around, but Z1 is always going to have a modulus of 3 and Z2 is always going to have a modulus of 2. And as I move them around, have a look at the modulus of their products, the number we get when we multiply those 2 numbers together. Let's see if you can spot anything here. So Z1 is always going to have a modulus of 3 and Z2 is always going to have a modulus of 2. Okay, so if I move that one around like that, so you can kind of see that. What's happening to that modulus of Z3? Well, you might have spotted actually it's always giving us an answer of 6. So the moduluses, or the moduli, if I'm going to be technical, of these 2 complex numbers when we multiply them together always seem to give us the answer 6 as the modulus of the product here, which is always going to work actually. So it doesn't matter what these moduluses were of the 2 original numbers. When I multiply those 2 numbers together, the modulus of the product, what I get when I multiply them together, is always going to be the product of the moduluses, if that makes sense. Okay, so that's a useful thing to know about moduluses. But what about the arguments? Now, the arguments, I think it's not quite so easy to see, but there is a pattern there as well. If I just sort of move these around a little bit further, and you can see here, let's just stop there. Now look at the argument of Z1, look at the argument of Z2, and then look at the argument of their product Z3. Notice what happens when you add these two arguments together. Now there's a bit of rounding going on here, so it doesn't look exactly right. But when you add those two arguments together, you get the argument of the product here. Let me try and put that somewhere else. Let me try a different number here, so you might be able to see that a bit better here. So can you see here that if I had 1.15 and add it to 2.28, I get 3.43. Okay, hopefully I'm convincing you that these arguments are indeed being added together. There's another one there. So can you see here, if I move this down here, actually let's move it around about here somewhere like that, and I'll move this one around so that we can see that a bit better, so it's not kind of on the screen there like that. There we go. Can you see if I add these two arguments together, we get the argument of Z3. So this leads us to a really, really useful fact, that if we want to multiply two complex numbers together, if we have them in modulus argument form, it becomes really easy to do. All we've got to do is multiply their moduli and add their arguments. Now, if you want a proof of this, there is a proof given in the textbook. I'm not going to give you a proof in this video, but what we'll do here is we will just kind of use that fact to see if we can answer a question on the next slide here. Okay, so here's the question for you then. We've got two numbers there. I've written them in modulus argument form. What you need to do to work out the answer to this one when we multiply these together is multiply their moduli, add their arguments, and then give your answer. Okay then, so have we got the idea? The answer to this one is going to be, well, the modulus of the answer is going to be the modulus here 8 multiplied by the modulus here 7. That gives us the answer 56. And then the argument of this one, we're going to add together the arguments of the two numbers we got here. So pi over 6 plus 2 pi over 3. I think that gives us 5 pi over 6 here like this. So in modulus argument form, there is my answer. Pretty easy once you know what you're doing, right? Okay, so what about if you're dividing complex numbers? Well, I'm sure it won't come as any surprise to you to know that when you divide complex numbers, those moduli get divided and the arguments get subtracted here, because we're just kind of undoing the process of multiplying, of course. So, of course, it's going to be the reverse of the multiplying process. And if you've got the idea so far, I'm sure that this question I've put on the screen is not going to cause you any problems here. But do pause the video and think about it, get your answer, and restart when you're done. So let's just have a quick look at the answer to this one then. So in modulus argument form, we can see that the modulus of this number here is 9. The modulus of the number in the denominator here is 2. So the modulus of our answer here must simply be 9 over 2. The arguments get subtracted. So we're going to take the pi over 4 and we're going to subtract pi over 3. And I think that gives us the answer minus pi over 12 as the argument of our answer here. Let's just finish off writing this in. Minus pi over 12 there. And that's the answer you should have got. Okay, so we've covered lots of really important stuff in this video already so far. Modulus argument form, but also why it's useful. And this idea of multiplying and dividing complex numbers which are in modulus argument form becomes a lot easier when you're working in that form. One final question though before we can finish this video. I've put a number on the screen here. It's not in modulus argument form, although it looks very, very close to modulus argument form. I'd like you to just pause the video and try and work out why the number there is not in modulus argument form, and then put it in modulus argument form before you restart. Okay, so what do you think here? I've written the number here again. And the problem is the fact that we've got a negative number in this position here. Of course, a modulus of any complex number has to be non-negative. It can't be a negative number. So that's the issue here, and you've got to watch out for this kind of thing, because quite often you might see numbers which are written in what looks like a modulus argument form, but they don't quite work because you've got to like maybe a minus sign in here. Sometimes you might see the minus here as well. It doesn't quite work out in the same way, so you do need to be on the lookout for that sort of thing. So that's the reason why it's not in modulus argument form. How can we put it in modulus argument form? Well, let's see if I can just sketch the Argand diagram here to find out where this number actually is. Pi over 8, well, the angle pi over 8 would sort of take us up in this direction here with an angle of pi over 8 here, but because we have a negative number here, we're actually kind of going off in this direction down here. So our complex number z is actually sort of down here. It's 5 units away, so we can say that the modulus of the number z here is 5, but the argument is actually going to be this angle here. Okay, so if this angle here is pi over 8, I think we can say that this angle round here is going in the negative direction, so it's going to be negative, and using a bit of sort of symmetry here, that angle there is the same as that angle there, pi over 8, so this has got to be minus 7 pi over 8 is the argument. Okay, hopefully that made sense. Let's just finish off quickly then by actually writing the number in modulus argument form. So the modulus is 5, and the argument is minus 7 pi over 8. Plus I times sine of minus 7 pi over 8. And there I've written the number in actual modulus argument form. Okay, and we have now reached the end of the video. There's a lot of really important stuff in this video, in this section of the chapter. So please do make sure that you are consolidating and making sure you're getting really fluent with these ideas by having a go at the exercises that I've put on the screen there. For now though, that's the end of this video, and I'll see you again next time.